In this tutorial, we will explain the different losses included in a PV-Syst simulation. All loss parameters are predefined by PV-Syst as reasonable default values for your early simulations. These correspond to standard systems. You may modify them according to the specifics of your system. The main parameter which should be adjusted according to the system configuration is the thermal behavior. The thermal balance involves the heat loss factor, which is known as U. It's equal to UC plus UV times the wind speed. U has the units of watts per square meter per Kelvin. In practice, we advise not to use the wind dependency UV, as the wind speed is usually not well defined in the Meteo data and the parameter UV is not well known. Therefore, we will set UV equal to 0 and include an average wind effect for the constant term UC. You can always press F1 for detailed information in the help. The main parameter needed for the wiring loss of the PV array is the resistance of the circuit. This induces a power loss which may be evaluated as a percentage of the system power at STC conditions. The button Detailed Computation provides a helpful tool for the calculation of the resistance according to the wire lengths and sections. This can be set for wires between modules, junction boxes, and the inverter. It is also possible to include the losses between the output of the inverter and the injection point or energy counter. You only have to define the distance and the wire section. The loss will also appear in the loss diagram. For big systems in the megawatt range, you can include losses in the external transformer circuits. The aim of this parameter is to reflect the confidence that you put in the matching of your real module set performance with respect to the manufacturer's specification. The default PV-Syst value is half the lower tolerance of the modules. The light-induced degradation happens in the first few hours of module exposure to the sun for P-type wafers only. Typical values are around 2%, and this sometimes appears on the datasheets. By default, PV-Syst does not take this loss into account. Module mismatch losses come from the fact that the modules in an array do not have the exact same IV characteristics. In a string of PV modules, the worst module drives the string's current. Detailed Computation is a pedagogical tool that will help you understand and calculate the module mismatch losses. The tool Strings Voltage Mismatch provides a pedagogical description of the principles of different mismatch modes. This shows namely that the current mismatch within a string is important because the current in the whole string is governed by the current in the weakest module in that string. The voltage mismatch between strings, on the other hand, has a much smaller impact on the system performance. According to our experience, the soiling effect is almost negligible in temperate, climate, residential situations. It may become very significant in some industrial environments like systems near railway lines or in desert climates. The soiling loss can be defined individually for each month to take into account periodical cleaning, rainy periods, or eventual snow covering. The incidence angle modifier loss parameter is normally defined in the PV module within the component database. You will, in principle, never modify it here. However, for very specific studies, you can define it using a standard profile based on Fresnel's laws or use a custom profile. The detailed study provides a complete tool for the analysis of the effects of the IAM during a full year. The auxiliaries consumption is the energy used for managing the system. This could be fans, air conditioning, electronic devices, lights, or any other energy consumption which has to be deducted from the PV produced to be sold to the grid. It is sometimes useful to foresee system failures or maintenance stops in the production expectations. You can define system unavailability as either a set of predefined periods, or ask for a random generation of these periods by defining it as a fraction of time. The spectral correction takes into account the changes in solar spectrum due to the scattering and absorption in the atmosphere. These changes depend on the water content in the atmosphere, the aerosols, and the optical path length of the light in the atmosphere, which is expressed as air mass. These spectral corrections depend on the PV technology. For crystalline silicon modules, the spectral correction is not necessary. It is almost insignificant. For cadmium telluride modules, PVsyst implements a correction model proposed by First Solar. The cadmium telluride correction model is the responsibility of First Solar. PVsyst cannot give any warranty regarding the calculations with this model. For amorphous modules, a parametric spectral correction has been proposed by the CREST and has been used for 15 years. This is part of the PVsyst model and has been checked experimentally at the University of Geneva.